2019 Senior Design Presentations for the University of Texas at Tyler. We are presenting groups from the Mechanical Engineering Department today and from the Electrical Engineering Department. I will proceed to introduce the first group, which contribute with an internal grant, TLA, and they design a system for our NE Lab 2. They're going to be able to present in 15 minutes what they have done for the last two semesters. Team number one. Are you guys ready?
Yes.
Please, let's start.
Good morning. My name is Grant Foster.
My name is Samuel James.
I'm Andrew Catalanato.
Elizabeth Terrios.
And I'm Todd Oakes, and we are Group 1, Double Pipe Heat Exchanger. We have designed a heat exchanger, stand, and data acquisition unit with educational use in mind.
As engineering students, we are required to have more than a basic understanding and knowledge of thermal processes and the changes that occur. Not just changes such as changes in temperature, changes in pressure. We were given the opportunity to come up with a design for a heat transfer device. As you all know, heat exchanger for the Mechanical Engineering Department here at UT Tyler. And with that, we're going to present today not only the shortcomings of what the current device that is currently being used in our mechanical engineering lab, but also with our device, we're saying that it's more ideal design for the thermal processes, and it also has unique, accurate, and universal components. I'm now going to turn it over to Samuel to talk about our scope.
Thank you, Elizabeth. So the scope of our project was simply to design a double pipe heat exchanger that will be housed in a sturdy stand, integrated with a set of sensor parts. Now the final component to our scope was to design a user interface that would be controlled through LabVIEW software. Now at this time I'm going to hand over to Todd to talk about our current system.
So the current system pictured has two tanks that mix inflow and outflow freely, resulting in very difficult calculations for beginning heat transfer students. The unit is fully proprietary. It has no replaceable parts, or without replacing the whole unit anyway. There's no way to digitally acquisition the data. There is only a small digital display on the front that provides you with 4 temperatures, and that is it. And here's Grant to talk about our design objectives.
Thank you, Todd. The objectives for this project were to design the end caps for a double pipe heat exchanger with the purpose of the end user in mind, that being the student. And that student will be able to interchange the inner pipes of various length, thickness, and material for the purpose of heat transfer analysis. In addition to that, because we are also working with the heating and the cooling side, you guys will see here in a few minutes, we are also designing within the system requirements the operational parameters of pressure, flow, and temperature. So through the development of our design, we went through approximately 5 iterations from design, rapid prototyping, to testing. Each test we were able to learn the strengths and the weaknesses, what was working and what wasn't working from the previous design. We were able to implement those strengths into the next prototype, and we were able to find solutions to the limitations. Subsequent prototypes, we were able to overcome some of the problems that we were encountering, such as asymmetrical compression, proper material selection, and gasket and O-ring configuration. Now I'd like to introduce Todd, and he's going to discuss the final design.
So the final design features 2 end caps that are machined as separate pieces and then sealed together permanently after being machined. And then there is 2 replaceable O-rings that seal the machined end caps in with the 2 tubes, allowing the inner tube to easily be interchanged for any other material. Features of this design are, of course, the interchangeable tubes, along with being able to change the length of the tubes, pressure, flow, and temperature sensors that are not present in the current solution inside of the labs, and replaceable parts in case any of the sensors break or there's a small leak anywhere or one small component breaks, you can replace that without replacing the whole system. Here's Liz to talk about this.
So I want to talk about just something as simple as just a stand for a heat exchanger, and just kind of take you through kind of a journey of what we initially came up with and how complicated it can get really quickly. And then of course with all that complication is custom parts and things like that, so then we had to go back a reiteration and redesign a more simple vertical position that not only changes, but as far as it customizes, as far as reducing our custom parts, we were able to reduce it to, reduce it because it originally had too many excessive custom parts. It was impractical to, as far as to build, and then also every time you try to design something, you want to make it as simple as possible. And so we're able to do that by making it vertical and able to create some design flaws that we were able to overcome as well. And so then we were able to reduce it to where we only had 6 custom parts and the rest of them were able to come off the shelf. And of course that decreases our cost. Then we were able to run through SolidWorks and FEA analysis, and it was just to confirm that this stand that we had designed was able to establish some pressure, hold it in place, and make sure that it did not, of course, over exceed or anything like that as far as what pressure was applied and needed for this design. And so that confirmed it. So this was our final design for the stand. As you can see here, just some of the components of interchangeable, not only just with the interchangeable components internally, but also able to change the length. So we went with a larger one, and then now, as you can see, we're able to, with this mechanism, adjust and make that more of a universal component in the stand to fit this. I now turn it over to Andrew to talk about electrical.
Thanks, Elizabeth. For the electrical component of our design, the primary focus was the implementation of a data acquisition system. So this involved selection and integration of the appropriate sensors and data acquisition hardware to acquire pressure, temperature, and flow data, log it, and display it to the user. So the first phase of development was coming up with an overall conceptual layout for the design. Here you can see a flow chart where we have the process parameters being measured as they enter and exit the heat exchanger. Analog signals from our sensors are sent back to the data acquisition hardware where they're digitized and displayed on the user interface. So once we came up with the overall conceptual layout, we were able to start selecting our sensors. So we selected these based on their reliability, their accuracy, and their cost relative to our specifications. For the integration into the system, we use these NPT pipe fittings, which allowed us to place them anywhere in the lines leading to or from the heat exchanger. Also allows them to be easily replaced if one of them fails or is damaged. And it also places them in direct contact with the process fluid to be measured. So once we had selected the sensors, we chose our data acquisition hardware and software, which was the NI Compact DAC, which interfaces easily with our sensors, as well as the LabVIEW software. So after everything was selected, we came up with an overall system schematic, which provides all the detailed information of every termination, every connector, every wire, and every component of the system and how it all fits together, which then allowed us to assemble a working prototype. So here we have an image of the data acquisition user interface, where all of the data is cleanly displayed for the process parameters, separated out by parameter and by location on the heat exchanger, where we have a graph of temperature, which is the primary focus of the heat exchanger labs. So with that, I'll turn it over to Todd to talk a little bit about the actual versus experimental results.
So we performed a computational fluid dynamics analysis to analyze the flow characteristics of our end caps. As you can see, there is a tiny bit of stagnation up in the top or bottom left corner. However, when we constructed a prototype, we inserted bubbles in the line and did not find that the circular rhythm or stagnation was occurring inside of our tubes. When we analyzed the results, we found that the heat transfer was pretty close to our measured heat transfer was pretty close to what we expected through Autodesk CFD. The difference in pressure can be explained by the difference in actual and assumed surface roughness.
So with regard to cost, as you can see in the graph, a significant percentage of the cost incurred during our project was in the design phase. As you can see, the prototype here cost over $140,000. We have been working since September of last year, and when we factor in the amount of time used in manufacturing, this prototype came out to $140,000. Now, when we consider mass producing the exact unit, the cost came down to $5,000. Now, with regards to safety, since this equipment will be used in a learning environment, we decided to design a stand that is durable and stable and will support the heat exchanger and will not fail during labs. We've also adopted an adequate cable management system. And one of the things that really excites us about the software is we have been able to incorporate a visual warning signal into the software, where if the set parameters are being exceeded, the software will issue out a warning signal. At this point, I'm going to hand over to Grant to talk about future considerations.
Thank you, Samuel. So through due to time constraints and the many iterations that we had of our prototype, we were not able to have the in-caps machine. That is certainly one of our future considerations. Remote access is also something we want to look into, and that would look like one of the professors, Professor Biswas or Professor Garcia, will be able to access by monitoring or observe the system through his laptop from across the room. At the moment, it's hardwired into the system. In addition to that, we would also like to, at some point, to automate the drain valves. So during this second semester of senior design, we have been able to implement some aspects of our design, in particular the heat exchanger, into several of the ME Lab 2 experiments, in which some of the junior level students have been able to do their experimentation and analysis using our design. So we do believe this is a viable design through proof of concept, in addition to our economical feasibility analysis and what we believe is a significant target market. So in conclusion, we want to end our presentation. Thank you guys for being here. We want to open the floor for any questions.
Could you state for me exactly what the problem statement was that led up to the overall project?
As far as what the inadequacy of what was being
Yeah,
done.
what is your overall problem statement for this project, right? So you went into your scope, but your scope looked more like a methodology than a scope necessarily. So I'm wondering, like, what was the problem statement for that project?
The problem statement was that this one, the two fluids mix after time, so you don't keep them separate. So the hot fluid eventually mixes with the cold fluid, so the inlet fluid is actually getting warmer. It doesn't stay consistent in the existing units. So, because as soon as it goes through the heat exchanger, it's a cartridge, so as soon as it goes through the heat exchanger, it's actually going back in there, and so then there's mixing going on. It's a very short, as far as analyzing the whole overall process. Okay. And so with that, and that's why we were trying to change it, is the problem statement was that it's a cartridge. Anything goes wrong with that, you have to replace that cartridge. And so here, if there's like just one of the sensors goes out, you just have to replace that one sensor. That cartridge, it runs from anywhere from $2,000 to $3,000 per cartridge. This sensor, is a fraction of that price. And so that's what it is. And also the fact that, we are able to, as Todd pointed out, able to do a change in pressure. Those components are not able to give you a change in pressure. You're not able to analyze a change in pressure. This one you can.
Good.
Next. Yes, ma'am.
So y'all talked a lot about the
Okay, so as far as the end caps go, we only have one annular, for the whole outer tube here, we've only got one place where we can let the water in. So we needed some way to distribute that water all the way around the tube so it wasn't just falling down one side. Otherwise, it would be even worse of a heat exchanger than a normal double pipe heat exchanger normally is. Yes?
Your controlling system, the lab view and software, is it driving or is it just picking data and displaying?
So it's a data acquisition system.
So no drive. When you want to drive the system or start the experiment, you have to do some manual work in there.
That is correct. So we have the data acquisition system and the actual heat exchanger and stand are the scope of this project. There are separate projects that are controlling the flow of the hot water and the cold water.
Is it a separate team?
Yes.
Okay.
Yeah, so there are 3 teams.
Is there a plan to merge them?
There is a plan in the future, and the hardware is capable of being merged, and the software is designed to be able to be incorporated.
One further question on the software. So you're acquiring the data, pressure, temperature, and flow rate. Are you doing any further analysis downstream, or you're just presenting it?
So it is got a button for logging the data, so you can output all of it to an Excel file and then analyze it from there.
But the software itself doesn't do the analysis.
That's correct.
Thank you.
Any other question? I would like to clarify something before you guys continue for the audience, which is part of the confusion. Whenever you start, you maybe as a courtesy would be, well, we're part of several teams. We are just in charge of the heat exchanger. There will be another team in charge of the heat generation cycle and another team in charge of the cooling cycle. We will give a little bit more of an idea of what portion of the things we're taking and for them to expect what is coming. Thank you very much.
I agree with that. When you started, that's why I asked the problem statement right there. I'm trying to figure out what was it that you were after and did you accomplish those goals? And there was a little bit of a disconnect there. And he's right. If you would have explained that, then that would have phrased that for